Alright, so we're going to demonstrate how pulse width modulation works with the DC motor. So what I have here is a DC motor on that faceplate, and on this oscilloscope here I'm going to show the drive voltage that I'm applying to it. Now the drive voltage is coming from this amplifier that we've built in the back. So this guy consists of the two MOSFETs that we've talked about, the two ideal switches. Alright, those two guys there are switching back and forth to apply a voltage to the motor, and I have a DC power supply over here set at 13.7 volts, which is connected to those transistors. Okay. Now, pulse width modulation signal is being passed to those transistors from a function generator. Okay. So I'm going to first try this at a very low frequency, at 1 hertz. So let me apply the voltage. Okay. So there you can see on the oscilloscope, you see the voltage that I'm applying, and you can see it going on and off and on and off at a rate of 1 hertz. And you can see in the background that the motor spins for a little while and then stops, spins and then stops. And it basically aligns with that waveform shown in the bottom. Now what I'm going to do is I'm going to change that frequency significantly. Okay, so let's take a look. So down here, I changed the frequency to 1 kilohertz. Okay. Now, on the oscilloscope here, I zoom out so I can see that drive. So notice now I'm at 500 microseconds per division, and I can see a very smooth motion to that. He continues to move. All right. Now, at this point, the machine speed is basically constant. Okay, he's not starting and stopping. In other words, he's not responding to the on, off like he was before. In this case, he's only responding to the DC input. So in this case, what I want to do is I want to change the duty ratio. All right. So in this case, let's take the duty ratio to 10%. Alright, now I can see a very slow motion on this guy, and you can see that I have about a 10% duty ratio on my drive. Now if you notice, this guy does tend to speed up a little bit as he comes around the top. See, there he goes. That's actually as a result of the loading on the machine. Alright, it's a little bit beyond where we're at the moment. Okay. Now if I increase the duty ratio, this guy should go faster. So let's go back over to here, and let me go to 90%. Alright, now I can see that waveform's high about 90% of the time, and I can see a fast motion. Alright, so clearly this guy's only responding to the DC component of the voltage. Right? What's happening now is because I'm driving this so fast, and particularly fast relative to the time constants of the motor, what's happening is the motor doesn't get much time to slow down in these little off times right here. Okay? Just like we talked about with the low pass filter behavior. In this case, I've got a low pass filter with the input being this voltage and the output being the speed of the machine. Okay? So as long as we make sure that this frequency here that we apply to the machine is significantly higher than the time constants of this thing, then he's only going to respond to the DC component, and all of the harmonics of this waveform will not be passed by the DC machine.